Today, I'm going to present CPU ray tracing of tree-based demo data. The motivation of this work lies in actively visualizing tree-based demo data from HPC simulations. For example, the NASA X dataset. The core video on the left is presented on Supercomputing 2017. To visualize the data back then, Patrick needed to extract a huge amount of triangles offline, which are then rendered offline in a second step. How to provide a native support of such data in existing visualization tools remains a challenge. In this work, we'll address this challenge. The video on the right indicates that we can produce an interactive, high-quality visualization of the same dataset in Osprey ray tracing library. In the literature, some work has studied for visualizing block structured MR data. Those general-purpose visualization tools now support rendering block structured MR data. However, they do not necessarily extend it well for tree-based MR data. Recently, a few works focus on supporting tree-based MR data in VTK. They proposed the VTK hypertree. However, it is unclear on how to directly perform interactive ray tracing on top of the presented data structure. Generally, MR data can be divided into two categories. Block-structured MR data are stored as successively final uniform grade. The grades overlaps at the final region, thus cause more memory footprint, but easier to process. While tree-based MR data are represented as trees, in which any workflow can be refined when more details are needed. To enable interactive rendering large datasets, we use a sparse arc tree to represent our data. Each node is represented with a 64-bit descriptor and the value range of its children. For leaf nodes, we pack the data value directly in the descriptor. For inner nodes, we store a 8-bit child mask indicating which of its 8 potential children exist, and the 55-bit child offset to its child node. To accelerate both implicit ISO surface and volume rendering, we also store the value range as a pair of floats for each node, for an additional 64 bits. To construct a continuous field, we propose generalized training interpolation to stitch across the level boundary. In GTI, samples that fall into the dual cells can be computed by simply performing training interpolation within the dual cell. For points at the level boundary, we interpolate the value within octants. Thus, the key remaining challenge is in how to initialize the octant vertices to achieve smooth interpolation. Here, we introduce virtual unstructured elements to initialize the vertices. Given the refinement factor of 2, each vertex falls into a fixed location with a limited number of such elements. There are 5 elements in 2D scenario. Before the initialization, we will need to pre-compute the weights of each case. As on how to pre-compute the fixed weights, we refer you to the paper. To provide an intuitive understanding, we begin with a 2D example. Sample point P is contained within an octant at the final site, within which we wish to perform binary interpolation. To do so, we must initialize the octant vertices. The value of O0 is known. The other 3 vertices lies on the final side of the level boundary and must be set to interpolate smoothly with the data on the causal side. OXY locates at the corner of the octant and is contained within the polygon formed by the cell center A, B, C, and D. To compute the value of OXY, we introduce the virtual unstructured elements as shown in case 4. The computation of the value for OX and OY are symmetric. Both vertices lie at the middle point of the octant on the causal side. Therefore, the value of OX is then the average value of OXY and OX prime. The computation of OX prime falls into 2D case 1. In 3D, stitching across level boundary is more complex. However, The deduce is similar with the 2D case. P is located in the right up far octant of the cell C. If cell 1 is refined, the data point that used for interpolation will be the green point rather than the black point 1. In this case, the set vertex of the octant OX is then shared by 5 cells and enclosed in the pyramid. We then interpolate along the base of the pyramid to form 2D case 1. Similarly, each edge vertex of the octant, for example OYZ, is shared by 4 neighboring cells. Depending on which neighbors are refined, the interpolation can be simplified to 2D case 2 to 5. For the corner vertex, OXYZ is shared by 8 neighboring cells, and 20 cases emerge for computing its value depending on which neighbors are refined. Note that the weights can be reduced and need to be computed only once. For rendering, we develop an extension module in ASPR ray tracing library with both volume and isosurface rendering. However, ASPR 1.8 volume rendering is built on taking a big step size and does not support adjusting the opacity when changing the step size. In our implementation, we modify the render to support traversing and integrating the volume over a given ray interval. We use a standard front-to-back arc ray traversal. The nodes are skipped if the volume range is entirely transparent, and the integration step size is adjusted to the width of the leaf cell being sampled. For isosurface rendering, we use implicit isosurface ray tracing rather than explicit isosurface extraction. Based on the data layout, the naive approach is generating octants using our GTI method and performing the ray iso injection over the octants. In this approach, each vertex will be computed for 8 times since it is shared by 8 neighboring octants, and thus is very time-consuming. One optimization involves using dual cells in the non-boundary region rather than octants. A dual cell in this region is enclosed with data points of no value, so no costly reconstruction kernel is required. However, both approaches perform the extraction over all input cells. This is inefficient since we will process a cell anyway, even if the isosurface does not pass through this cell. An additional optimization would be to consider only active cells. We donate a cell as an active cell if the value range of this cell and its neighboring cells overlaps the ISO value. The performance improvement of those optimizations will be reported later. We evaluate our system with 5 datasets. Of particular interest for the synthetic data is that we can define a test function over the mesh and get a reference result to compare isosurface reconstruction quality with. We benchmark our system on FSM, which is a quad socket workstation with 72 physical cores. This figure shows a screenshot of the volume and isosurface rendering of 4 real-world datasets. It indicates that our system is capable of providing interactive, high-fidelity visualization of tree-based stemma data. In the experiment, we first evaluate the functionality of our GTI method. We compare the image quality with 4 existing methods, using the synthetic data and 2 real-world datasets. For synthetic data, isosurfaces in the reference image are generated from a uniform grid using channeling interpolation. Isosurfaces in other images are generated from an adaptive mesh. The results show the GTI method produce a crack-free isosurface that is visually closest to the underlying data. When testing with the real-world dataset, the GTI method produces the highest quality isosurface. Next, we compare the rendering performance and memory consumption when using the ASPR unstructured mesh renderer and our module. The unstructured mesh renderer takes a fixed step size. Generally, A low sampling rate will result in higher rendering performance at the cost of image quality. In these slides, the frame rates are listed in the table and the output images are shown. When using a high sample rate, the unstructured mesh render produces images with similar quality to our module, yet our frame rate are comparable or higher. By contrast, when using a low sample rate, our module can render images of higher quality while maintaining comparable frame rate. In addition, the memory consumption of our module is way lower than the reference render. When rendering isosurface, we benchmark the extraction time with the proposed optimizations. From this table, we see that the optimizations hamper the performance for a small dataset. Performing those optimizations does take additional compute time, which on small datasets may not pay off. However, they performed much better than the naive approach when it comes to medium or large datasets. The speed up of the two approaches are 2 to 5 times and 16 to 27 times respectively. We also plot the extraction time with active cell percentage. Our extraction time increased only by 8 times when the active cell percentage goes up by 56 times, likely due to better memory access patterns. In conclusion, in this work, we proposed a novel reconstruction method, GTI, for artifact-free visualization, and an efficient visualization solution for tree-based metadata. In addition, we integrate our GTI methods into Osprey and open source release the code. In the future, we wish to extend the work with distributed rendering and in situ visualizations. We would also like to provide a more compact representation of the data structure. Finally, we want to integrate our work into OpenVKL and ParaView. Thank you.